Hello everybody. We're still talking about the absorption using Microsoft Excel, and in this video we're going to talk about one thing which is important and we face it a lot, which is the stage efficiency. So to understand the stage efficiency, we have to understand what we were doing before. So in the previous videos, we assumed that each stage is a theoretical stage, which means that the two streams coming out of the same stage are in equilibrium. And that's why we were able to go from operating line to equilibrium curve, back to operating line and equilibrium curve, and so on until we reach at the end of the stages. But this is a very theoretical assumption, and it's not realistic, because to do this or to achieve this separation that will make the two stages coming out of the same stages and the stage in equilibrium means that we are leaving them for very long time, and we are offering very large surface area so that we will have the mass transfer coming until it reaches its end, and this will never happen. And that's why we used to do what we or to calculate the number of actual stages using the overall efficiency, which is this parameter that we use to divide the number of theoretical stages by the efficiency to get the number of actual stages. So this is one way we can do the calculation so that we can get some realistic values instead of getting the ideal values, which are not realistic, as we mentioned. One other option is to do the efficiency, instead of doing it for the whole column, to do it for each stage separately. And this this is not gonna be something that will be done using the tray-to-tray calculations, because as we mentioned before, the tray-to-tray calculations is a very time-consuming and difficult method to do. So we will do the stage efficiency or take the stage efficiency into consideration while doing the graphical solution. And to understand how we will do this, we need to kind of revise quickly what we did and how we can take into account the efficiency while doing the counting of the number of stages. So this is stage number 2, for instance, and it has the vapor coming out of the stage number 1, which is has Y1, the mole ratio of the solute, and the stream coming out as with mole ratio of Y2, and the liquid coming from stage 3 has mole ratio of X3 and coming out of the stage at the mole ratio of X2. So X3 contacts Y2 and X2 contacts Y1, and Y2 and Yx are coming of the same stage. That's why they have the same number. And this is what we did here when we drew the operating and equilibrium curve and drew the stages while doing the counting of the number of stages. So here we have point Y1 and X2, which represents this part. We have the two streams in contact with each other, starting to do mass transfer. That's why they are in the operating line. And the assumption that we made is that these two stages or two streams did the mass transfer until X2 and Y2 came out of the same stage in equilibrium. So X2 and Y2 are in equilibrium, and that's why they lie on the equilibrium curve. And then the liquid with or the vapor is coming from here, contacts the liquid with mole ratio of X3. So the point that I want to focus on is that this point X2 and Y2 lies on the equilibrium curve, which is not true. And that's why I'm calling it here Y2 ideal, because this is an ideal value, it's not an actual value. So what should happen is that I will not reach this point starting from Y1. I'm not gonna reach Y2. I'm gonna reach a point in between Y1 and Y2 ideal, which is the Y2 actual. The Y2 actual is the actual mole ratio of the vapor coming out of the stage number 2, and this is gonna be before or it's not gonna be equal to the Y2 ideal due to the mass transfer and time limitations that we mentioned before. And so the efficiency of the stage is the actual separation, which is this difference, divided by the ideal separation, which is this difference. So it's this divided by this, which is going to be mathematically described as y1 minus y2 actual divided by y1 minus y2 ideal. And based on the information that we have, we can calculate the actual y2 because I know the efficiency of the stage, I know the value of y1, and I know y2 ideal because this is what I can get from the equilibrium relation. So I can get all of these values, and from this I can calculate y2 actual, which is y1 minus the efficiency multiplied by the actual separation. So this is what we're gonna do when dealing with this new piece of information using Microsoft Excel. So I'm gonna go back to the same file that we mentioned or we used before, and I'm gonna go ahead now and start calculating the actual Y or mole ratios based on the efficiency or the stage efficiency. One thing that we need to do is to or to plan for before we go ahead and start to work is to plan for the place where we're gonna put everything, and it's important to make your file as organized as possible because it makes your life easier. It makes the tracking of the information easier. So it's important to think where you're gonna put the new parameters that you're gonna calculate. So what I thought and what I think is better is to insert a new column here. I just need to keep this back, and this is where I'm gonna call this Y ideal, and this is gonna be Y actual. I'm sorry, just some formatting things. So for this Y actual, let's go back. Y1 is common in both the ideal and the actual separations. So Y1 is going to be the same, which is this Y, and this is going to be the same. So this is the actual values. And as you see, these two Y's, which are this and this, were calculated or equal to this value. So once, if I change this value, then these two should accordingly change. So I shouldn't change these because they're going to be calculated from the value that I'm going to calculate here. And this Y is the one that I'm going to calculate based on the new piece of information, which is the efficiency. So I would first like to put the stage efficiency here. I'm going to put it as 40%. Sorry. And I am gonna calculate it from this minus the efficiency. I'm gonna type F4 multiplied by the actual or the theoretical separation. So this is the value that I got, which is the actual composition or the actual, I'm sorry, mole ratios of the vapor leaving the first stage. And this value must be between these two values. So it has to be less than the y1 and larger than y2, because this is where it should lie. It should lie between these two. So this is kind of thing that you can use to check your calculations. And here these, instead of being calculated from this cell, are going to be calculated from the previous cell. And here you see there is some change. First thing is that this line should be drawn from here, and again for the same reason that I do not understand, it is disappearing. I hope if somebody can help me with this. I'm kind of stuck, and I did a lot of searches and I still cannot understand why the lines are the line color is none. So if you can help me with this, I would be really grateful. Anyway, so this is how we calculate the Y actual for the first stage. I'm gonna do this for the second stage. Again, it's 102 and 0.078, and this is calculated 0.092, which is in between these two, so it's working. I'm gonna copy this and paste this here. And now what I need to do is what I used to do every time, is to copy paste. We have many stages here, so I'm gonna copy like 3 and then paste them instead of pasting one by one. think this is all. I have now 10 stages, and you see, I'm not gonna do this now, but this is what I should do. I just drag this from here to here, and it should be done, but this is appearing, so I'm not doing it. But anyways, I've done this already for many stages. I did it for 20 stages. It's a very long process, but again, it's just done once, and you can change any parameter or any one of the inputs, and it's gonna update automatically. But the point that I want to make is that this is what I did. I calculated the output, the actual output out of each stage, and you see, after even 10 stages, I didn't reach the value that I reached in 6 stages before. What I did in the absorption video with the ideal separation. Here you had to go to y should be 0.006, like almost 16 or 17 stages. You see, this is where you have the fraction, which is the last stage. So I needed many stages more than what I used to need before. And here I do not need to do anything else other than adding all these values, and you have to like approximate it to the next or the larger integer. So here it should be 16.25, and it's calculated as 17. I did the sum and the ceiling in one formula because here I've already taken into consideration the efficiencies of the stages. One thing that I want to point out is that when we did the absorption with the overall efficiency, we used to need 6 stages, and I'm gonna put the theoretical. I mean, this is the overall efficiency. As 40%, I needed 16 stages, while here I needed 17. So they are giving really close values in case of theoretical and I mean the stage efficiency and the overall efficiency, they're giving close values. It might be easier to do this in some cases and easier. Usually the overall efficiency is easier, but sometimes the stage efficiencies are more accurate, and sometimes you can have different efficiencies for each stage. So some stages would go for 40, some stages would go for 35, whatever the value, but this might be more accurate if you have the detailed stage efficiencies. One thing else that, or one last thing I want to mention here is that I plotted this curve, which is the vertex of each one of these triangles. I put them together here in a table and I plotted them, and this is what we can call the new equilibrium curve. And this is something that we can do graphically instead of doing the calculations manually, is by drawing vertical lines between the operating line and equilibrium curve, and take 40% of this line width, I mean line length. So if it's 1 centimeter, then you get 4 millimeters, and then the same here. For each distance, you get 40% of this distance, and then connect these lines together, or these points together. And this is gonna be the new equilibrium curve that represents the 40% stage efficiency for your system. So this might be an easier way to calculate the number of stages instead of doing the calculations. Of course, in my case, I'm doing everything automatically. I'm just copying and pasting, so I'm not doing any calculations manually. But in case you are doing the calculations manually, then it might be easier to draw a new equilibrium curve, and this represents the stage efficiency, or the equilibrium under the stage efficiency conditions. There are two alternatives, and they're doing the same thing. So I hope it helps, and I'll see you in the next video, inshallah. Goodbye.